Hey everyone, I'm TK. I'm on the engineering side here at Yugabyte. I have with me Anton, who worked on some of the performance improvements, especially around the backward scan area. Uh, and this feature is available in the enhanced Postgres compatibility builds, right? So, Anton, the stage is all yours. Take it away.
Hi everyone. So I'm starting. So today we will shortly cover what are common scans in general, what are forward and backward scans, what is the current performance of backward scans in YugabyteDB before the improvement. We'll dig into backward scan improvement details and check the results of these improvements. I'd like to remind several terms which will be used today. So firstly, shortly about scans in general. So a scan is a process of examining rows in a table or in an index to retrieve data, or in other words, it is a way to access and retrieve rows from a table or an index. And there are different types of scans used to retrieve data. So for example, sequential scan reads every row in a table starting from the first row to the last row. Index scan uses an index to quickly locate the row that satisfies a query condition. And index only scan retrieves all the required information directly from the index without accessing the underlying table data, and etc. So I think there is no need to focus on this area because we are going to look into the scans from a different perspective. So another perspective is direction of a scan. So scan direction is the direction in which rows are accessed during data retrieval operations, particularly when using ordered queries or when navigating through indexes. There are two directions only. A forward scan direction retrieves data in the natural order of the records, typically from the beginning to the end. And it is commonly used when you want to retrieve records in ascending order. And also we have a backward scan, which retrieves data in the reverse order, typically from the end to the beginning. This is useful for queries that need to access records in the descending order.
Yeah, one clarification, Anton, even though you're saying from first record to last record, it could be within a certain range of
Sure,
primary keys as well, right? Not necessarily all the records in the table, right? Yeah.
sure, thank you. So here's an example for forward and backward scan directions. There is a simple table with a primary key on the first column, and several thousand rows are inserted, and a simple select on the primary key column with an ascending order will run in a forward scan direction. So we can see it on the left, and we can see that query plan contains index scan without any other words. And a slight modification of the same simple query by adding a sorting in descending order will result in a backward scanning direction, which could also be seen from the output of the explain analyze. So we can see on the right hand that index scan backward is used for this case. So this is a quick example of how it works. Okay, and now the final portion of the terms, which will be used today. So there are several methods which are used under the hood by forward and backward scans. The main ones are seek, prev, and next. And so a seek call is an operation that directly accesses a specific record or position. It's efficient because it jumps directly to the desired location without scanning through all the records. A next call retrieves the subsequent record following the current position. So if you're iterating through records, this could be the operation that allows you to move to the next entry. And the prev call retrieves the preceding record relative to the current position. It allows backward navigation through the records. And on the right hand is the example of this operation. So if we have, let's say we have a successful seek done by key 2 and this position becomes a current position, then doing a next call moves a current position to the next record marked with a blue color, and doing a prev call from the initial position moves the current position to the previous record marked with purple color. So seems quite simple. Okay, moving next. So now about backwards scans performance as of 2022.1. So based on the internal benchmarks, backward scans are from 4 to 11 times slower than forward scans. And specifically, RocksDB prev call is 5 times slower than a RocksDB next call. And this is a quite low level thing, which I'm going to talk a bit later. And as a result of such performance of backward scans compared to forward scans, the query layer works around backward scans in some cases, and if it's possible, by generating a plan that has a forward scan with a sort on the top to work around the fact that backward scans are slow. But such workaround has a side effects of an additional memory used.
Anton, one additional thing I wanted to add is some of our viewers might not know how Yugabyte is built. So just a quick recap, Yugabyte storage engine is built on RocksDB. So we use RocksDB to store the key value pairs for the docdb layer. And we have another layer on top called the docdb layer, which sort of like has a slightly higher level abstraction, which manages transactions and other things, right?
Right.
So since we have two layers, there are perf implications caused by one layer and the other layer as well, right? And so that's what Anton was talking about.
Yeah, yeah. That's what I'm going to cover a bit later. Then thank you. Thank you for the clarification. Okay, so moving next. Here's some background of backward scans. Um, just to remind, so TK already reminded that we have several layers, and let's say for simplicity, uh, consider the docdb layer operates with a table row and maybe builds a row from smaller pieces. We call it generally records, which are handled by the underlying rocksdb layer. And the only way to read and build a table row is to use a forward scan, even in case of backward scan direction. So as of 2024.1, there is no way to build a row in the reverse order, to read the row in the reverse order. So we have to read it in the forward direction only. And after we read this row, the iterator have to jump to the previous row because we literally ended up reading all the records, and now we need to go to the previous row. That's why we need to do additional jump. So, and this is how a seek call is used to position to the first record of a previous table row. So, and as a result, there would be one prev call, two seek calls, and some number of next calls depending on how many records are should be read for this table row. So I have some diagram. Hope you can see it good. So this is an example, some synthetic example. So let's consider we have a table with 6 columns. It has several rows inserted, and additionally, each row has 2 columns updated. So here they are marked as a call 1 and call 2. And we would like to make a um, backward scan. I mean, we would like to make a reading in the descending order, and this is how backward scan it will be used. And so the following approach will be used. So firstly, we need to jump to the latest record, like latest table row, because we are reading in the descending order. So the first seek is required. So it does not mean we will jump to the latest record every time. It depends on the query. Sometimes we need to jump to the particular key. So in this case, it will be seek to the key. And it will point to the very first record of the given key. So, but let's skip it for now. So we jumped to the latest record, to the last, but it will point like to the end of the record. But as I said, we can read only in forward direction. That's why it is required to jump to the beginning of the row. So from that last record, we can extract the full key, and using this key, we do one more seek to be positioned to the very first record of this table row. Sorry, table row. Generally, we have packet rows as a first record. So let's consider this for simplicity also. So we have a packet row and 2 updates. So for column 1 and column 2. So now we have to read all the 3 records to build the full row. And this reading is happening via next calls. Now, when we complete reading this last row, the cursor will be pointing to the end, to the something after the last record. So now we should read the previous row, but we cannot simply understand what the row would be. And that's why we have to firstly seek to the beginning of just read row again, make a paref call, see the step number 5. This will allow us to be located on the latest record of the previous row. And now again, as we have only forward scan to read the complete table row, we extracting the full key from this row, do again one seek to be pointing to the very first record, which is again a packet row in this example, and then we repeat the reading of this row using the next calls one by one. Sorry, and sometimes the next calls are not used because when we read the row, we will be naturally moving. But in some cases, like under the hood, it will be still called. So now when we read the second row, we will be pointing again to some key after, to some row after the current one, and we cannot do a pref call because we will be like pointing to the row we already read. That's why when you have to do one more seek, and only after that we have to do a pref call. So see, there are a lot of unnecessary actions, and like it sounds like not the optimal way for reading in the reverse direction. Okay, so here we come to the main part. So we have like 2 main improvements, and I'm going to talk about them now. So first of all, to avoid extra seek and next calls, we can try to build a row like from the end to the beginning in the reverse order. So just using the pref calls. And another improvement is related to the RocksDB pref call. So we can also try to improve this call, but I will jump into this a bit later to give more details here about this pref call.
Anton, one quick question. So since we do additional seeks in the previous implementation, additional seeks and next calls, does it also incur additional IO, or this is just in-memory walking of the.
Yes, it will take additional I/O because we are not necessarily have the data loaded into the memory. We could read it from the disk. We have to decode it, so on and so forth.
No, but after the first IO, you would have it in memory, right? So unless it
Right,
gets evicted, you would not necessarily do additional IOs for this back and forth, right? For
right,
the
right.
most part.
Okay, okay. So and the as said, the simple idea is just to try to build a table row in a reverse order from the oldest record to the newest record. So we can see the schema will become much simpler in this case. So we just position to the last record, and then we're just reading all the records one by one using the prev call and building the row. So no need to do any seek calls, additional seek calls, next calls. So sounds very good in this case. Okay. So
So
and
Anton,
he,
we
yeah,
have, sorry, if you go back to the previous slide, we have a question from the audience.
sure.
The representation that you have on the screen, is it a logical view of the keys in order? Uh, so typically, if the keys are updated, they would get flushed to the newer SSD files. So in this case, would the next perform another seek to the other SSD is a question.
Yes, this is a logical view. So it's just some simplified top level view on how we do reading. So under the hood, we have a, a big hierarchy of different iterators, and they are responsible for reading from files, from merging the data from these files, and so on and so forth. So yes, this is like high level view on how this is happening
Correct.
without low level details.
Correct. And also to add to it, like irrespective of whether the keys are coming from one SSD or multiple SSD, the algorithm that we used to perform a backward scan was inefficient, right? And so,
Right,
if I understand correctly, the focus of the improvement was to improve the algorithm to reduce the unnecessary overheads, and the gains would show up irrespective of whether the updates are within the same SSD file or
right.
across, right?
We this algorithm um, acts on the high level, so it
Right.
doesn't matter. It's let's say we already have read all the files, and it doesn't matter in this case. So we have some rows, they organized, sorted in some way, and we are working on top of this data already.
Correct.
Okay, so and here is the example, a simple query which showcases the differences. So we have a table with 6 columns, we have an index, and we inserted some data into the table. It contains 100,000 rows. So, and here I am doing the explain, analyze this, debug, our extended utility, which helps to check some additional params like metrics. And in case of improved backward scans are off, we will see that we're doing a lot of seek, a lot of next calls, and prev calls. The same way I showed in the picture. And in case of improved backward scans are on, we can see that we have no next calls at all, and number of seeks is much lower, and this is the reasonable number because we have 98 requests, so we have one seek per request plus one additional seek used for seek to last, and the number of prev calls is also looking reasonable. So yeah, and the execution time, so it like 3 times 4 times faster in this case.
Very cool. Hey, one thing I also wanted to add is I don't know if most viewers might be familiar with explain, analyze, dist, debug. It's one of the additional enhancements that we have added to explain, analyze. With a dist debug, you would sort of like get additional statistics from the storage layer, and that's exactly the thing that Anton has shown on the screen, right? And with this, you can get a better glimpse of, hey, how many seeks and next did my query take, kind of a thing, right? And those statistics are emitted for every operator in the query as well as the aggregate statistics for the entire query is dumped, right? So that's another thing that our viewers can benefit from.
Yeah, thank you, TK. So I would like to add also that it's actually really useful. I use that a lot of times in debugging different issues. So very helpful feature. So recommend for everyone. Okay, so moving next. Okay, so this is another example. So I've mentioned earlier that in some cases query layer may work around backward scans by doing a sequential uh, seek and then a sort. In this case, it's a bit different, but the idea is the same. So we'll assume we have enabled cost-based optimizer, and by default it will for the similar simple request it will pick um, index scan, it will be forward scan, and on top of the result it will do a sort in descending order. But if we enable the improved backward scans, we will see that the plan will be changed, and um, backward scans will be used in this case, providing the same results.
Yeah, thanks,
Okay.
Anton. There's a question from the chat. Folks are asking, we suspect the backward scan only works on index or fields that have ascending specified. I guess, Anton, you presented the example earlier in the presentation, but maybe you want to reinforce that. Hey,
Uh, should I move back again?
yeah, yeah. No, I mean, the query is there in this one as well. So,
Um, it actually depends. So,
I mean,
um,
basically,
in,
if the ordering of the table and the query is inverse, then we would
yep.
use backward
So,
scan.
in when we need a reverse order, it doesn't. In most cases, the explicit sorting will be taken into account. We have to specify it, but sometimes we can even create a primary key or other keys like secondary keys using this order. So yeah, in case of uh, planner decides we need a backward scan like
Right,
reverse order,
right,
it will use it.
right, right. Yeah, one thing I wanted to add here is even though there is workaround, like, hey, you can do a forward scan and then sort it in memory and then return the results in the order that was expected. There is a cost to the additional sort. There's additional memory cost, and right. So that was one of the other motivating factors to improve backward scans natively here, so that queries don't necessarily pay the additional cost of the memory.
All right, thank you. And here are the result of the internal benchmark for backward scans. So these some are internal workloads. So we can compare the latencies. The results became much better. So seems very nice results in this case for the improvement for the first idea. I mean this one, avoiding extra seek and next calls. Okay. Um, Moving next. Okay, so now we are jumped into the RocksDB specific. So as said, we have different layers. So um, this is a schema showing us a data block of a SST file actually. So just to remind, SST files are the uh, files in which we store all the data on disk on the storage device. So, and we are reading the data by data blocks. So,
So, Anton, there is a question
sorry,
in the
missed it.
chat. That's okay. So the question is, if we have an order by some column descending in a lot of queries, right? Is it recommended to create an index with that column and include it in the index with descending specified, or would your feature essentially avoid that, right? So that's a question, I guess.
This is a good question. Thank you. Um,
But that's essentially the TLDR, right? Like people don't
yes,
need to use the workarounds. They can. I mean, that was a whole motivation to improve backward scan so that the native backward scan is as
right,
good as the forward scan, right? So they no
right,
longer, when they get their hands on this, they would no longer need to do additional things, right?
right, right. Thank you. Okay, so moving back to the data block. So a couple of words about the structure of a data block. So each data block consists of some number of restart blocks, and the restart block is just a like group of records in this block. It's like and for a data block, it is possible to seek only to the beginning of any restart block. So the restart block is like a minimal unit we can read from a data block. And forward reads are required to navigate inside this restart block if we need to read a key inside this block. So we can seek to the beginning of a restart block as shown here, but inside the block we have to use forward read. And by default, so restart block again consists of some number of consecutive entries. By default, its number is 16. So we are not recommending to change it generally. So the very first entry contains a full key. All other entries contains a delta between the entries key and the previous key. So it actually there are different algorithms we use for delta, but just let for simplicity it is some delta of the key. And thus to get to a 15th entries key, it is required to read and decode the first entry, and then read, decode, and apply all other key deltas. So yeah, so and as an example of backward reading of over this restart block, then the first step would be to read the 16th entry. So assume we have 16 entries of the restart block, which will require reading all the entries from the very first entry up to 16th entry and apply all of 15 deltas. The second step, so when we are moving back, when we're doing a pref, we again have to start from the very first entry, read up to the 15th entry, apply all the deltas, and we get the full key. Now, when we do one more pref call, again, we have to read the 14th key, but again, we can read only from the beginning, and we repeat this again and again. So while we are doing the iteration backward, reverse iteration of the restart block, we always have to read the full key and apply all the deltas. Oh, sorry. Um, and this is kind of a disadvantage and a bottleneck here because there are a lot of repeated operations we have to do. And like the obvious solution is to try to cache the keys when we do a first pass over the restart block. So in this case, we pay the cost of reading and decoding of all the entries inside the restart block only once, only during the full first pass. And yeah, that's fine. But the
But,
trade-off here is that we have to use additional memory to store all the keys
but
of the 16
yeah.
keys. instead of storing one key. But the memory will be released once iterator moves to the next restart block.
Anton, sorry to interrupt. A quick time check. I think we might skim through the perf and then move to the demo. Yeah.
Okay. So just quickly, so we have some results for internal benchmarks. So we can see that the fast pref becomes much better. So almost quite close to the forward scan, but still a bit far. Comparing like 5 times faster comparing to the previous results. So this is good. And now these are the results when both improvements are enabled. So they're actually, you can check later, they're 10% better approximately comparing to the first improvement only. So and finally, the comparing to the forward scans, so we can see that the improved backward scans become really faster in
Almost
this
on
case.
par, right? Almost
Yeah,
on
yeah.
par. Yeah.
Okay,
Cool.
so yeah, and current state. So it's quite important, I think, about the flags. So the feature is available in 2.23.0 in the preview mode. So in this case, this means you are not allowed to turn the feature on using a like simple action of setting a flag. You have to update two flags. So there is a load preview flag CSV. It has to contain these use fast backward flag, and then you can set use fast backward scan to true to try the feature. Also, there are a couple of advanced flag, but they're generally not required, just to be aware of them. And the feature would be enabled in upcoming stable release by default. Okay, so a quick demo. Give me a second, I'll share my screen. Okay, so I already have a simple cluster created, RF1. Now the feature is disabled, I think. Okay, we have one table. This is from the slides. It has 6 columns and an index. So now I will do a example of backward scan reading. Okay. So yeah, this is the fast version. Sorry. So we can see from the plan that we have the index scan backward used. We have 98 requests. Almost all the rows are scanned, and we can see that we are doing only seek and pref calls. So the execution time is 88 milliseconds. Okay, now I am restarting the cluster quickly without the flags enabled. So here the feature will be disabled. Let's wait a second. Okay, now let's try to do the explain analyze one more time. Okay, yeah, and this again, this is a backward scan, but we can see that we have a lot of next calls, a lot of seek calls, and the execution time is much worse, like 4 times worse.
Right.
Yeah, seems good.
Yep. Thanks, Anton. 4x benefit. It's amazing. Thanks a lot
Thank you.
for presenting this work to the users. I'm pretty sure it will help with all the workloads that are using backward scans tremendously, right? Yeah.
Okay, thank you. Thank you
Thanks,
for your attention.
Anton.